Hello and welcome back, and in this tutorial we are going to talk about the proof of some trigonometric identities with the concept of vectors. My name is Dr. Garma Abdisa. Let us start our discussion with examples. For example, show the trigonometric identity cosine of alpha minus beta, which is expanded as cos alpha cos beta plus sine alpha sine beta. Most of us may have used this kind of mathematical identity a number of times, but we may not know where it came from. And in this tutorial, I will show you the proof in relation to the concept of vectors. Let this be our Cartesian coordinate system. I will only consider, for simplicity of the problem, I will only consider the xy coordinate system. And let this be a vector B, and let this be a vector A. Let the angle at which vector A is from the positive x-axis is angle alpha, and the angle of vector B from the positive x-axis is beta. So the angle between the two vectors is therefore alpha minus beta, as you can observe. Then we can expand the components of A as AX is equal to A cosine of alpha, and AY is A sine of alpha. And AZ is 0, of course, because we are only placing our vector only on the xy plane, and the z component is missing. And the component of B can be found to be Bx is equal to B cosine of beta, and By is B sine of beta, and the Bz is equal to 0. So these are our two vectors. So A dot B is AX BX plus AY BY plus AZ BZ. By the way, I have also made a proof of this relationship for the dot product on another video, and you can have a look at that. And A dot B is therefore, by directly plugging in everything we have into this formula, becomes AB times cosine of alpha cosine of beta plus AB times sine of alpha sine of beta plus 0. So from the very basic definition of the cosine of the dot product of any two vectors, we also have that A dot B is equal to magnitude of A times magnitude of B times cosine of the angle between the two vectors, which in this case is alpha minus beta. So for the dot product, we have two formulas. One is based on this AX BX plus AY BY plus AZ BZ, and the other one is the very standard definition of the dot product itself, which is A dot B is equal to the magnitude of the product of the two vectors times the cosine of the angle between the two. So by combining these two, and by deleting these AB terms, then it turns out that cosine of alpha minus beta is equal to cosine alpha cosine beta plus sine alpha sine of beta. And the cosine of the difference or the sum of angle always goes as if we have a plus minus here, it becomes a minus plus there, which our result also agrees with it, in that it is a minus here and it turns out to be a plus there. The second example shows the trigonometric identity sine of alpha minus beta is equal to sine alpha cosine beta minus cosine of alpha times sine of beta. Once again here, I want to place my vector on a Cartesian coordinate system, xy system, whereby this is my vector B and this is my vector A, pretty much same way as we did before. This is at an angle alpha, and this vector B is at an angle beta, and the angle between the two vectors is actually alpha minus beta, which is the difference between the two angles. And the components of A is AX is A cosine of alpha, and AY is A sine of alpha, and the AZ is 0. In a similar way, the components of B become BX is B cosine of beta, and the BY is B sine of beta, and the BZ is actually 0. This is a very straightforward and very similar to what we did in example 1 as well. So the cross product of these two vectors, A cross B, is always defined to be AY BZ minus AZ BY in the I plus AZ BX minus of X BZ in the J plus AX BY minus of AY BX in the K. By the way, I have made a very distinct proof, and there is a video post for this, and you can have a look at it if you don't know or if you are not sure where this has come from. But for now, I will directly substitute in those given components for the A vector and for the B vector into this formula to find the cross product. And it turns out that because the z components are already missing, everything containing the z term will disappear, and we are only left with this last k component of the vector, and a cross b reduces to ax by minus of ay bx in the k direction. So upon direct substitution of these values into my last simplified result, a cross b now becomes a cross b is equal to ab into cosine of alpha times sine of beta minus sine of alpha cosine of beta in the k direction, in the direction of k unit vector. This is what we have found. And from another very basic definition of the cross product of any two vectors, it turns out that the magnitude of the cross product of any two vectors is the product of the magnitude of the unit vectors times sine of the angle between the two vectors, and the direction is to be determined using the right-hand rule. And in this case, and I will show you a few minutes later, that it is in the negative z direction. That's why a cross b becomes minus of ab times sine of alpha minus beta. So by combining these two alternative approaches to find the cross product of the two vectors, and by cancelling out this common term, which is AB, it turns out that sine of alpha minus beta becomes sine of alpha cosine of beta minus cosine of alpha times sine of beta. And the sine expansion for the sum or difference of any two angles always turns out to be sine of alpha plus or minus beta becomes sine alpha cosine beta plus or minus cosine of alpha times sine of beta. And as I promised to you, using the right-hand rule, if you curl your finger from A towards B, your thumb points into the plane of the screen that you are watching now. So it means that the z-axis is from this origin towards us, and the negative z component is from that origin into the page. So by curling your finger from A towards B, your thumb will point into the page or into the plane of the screen that we are watching. So that is actually in the negative z direction. So a cross will be into the page and hence negative, and that's why I have used the negative in the proof. And the third example is that if the resultant of three vectors a, b, and c is 0, as shown in this diagram. For example, this is vector a and this is vector b. If this is a vector c, that would be the sum of a plus b becomes c, because now c is taken as a resultant, or the vectorial sum of a and b. But rather, what would happen if my third vector c is in the reverse direction? Because c is in the reverse direction to that resultant, it turns out that we will write a plus b plus c is equal to 0. So this is what the problem says. The problem says if the resultant of three vectors a, b, and c is 0, that is in this arrangement, so what we are required to show is that the vector a, let me show you the angles first. So the vector a divided by sine of an angle which is opposite to this side, which is sine of alpha. Vector b divided by an angle which is opposite to this side, which is sine of beta. And vector c divided by an angle which is opposite to that, which is sine of gamma. And this is clearly the sine law. So this is simply a proof of sine law based on the vector concept. So this is the given arrangement for our problem. Have a look at it. This is actually the problem. So the solution is, assume this is our vector A, and if this is our vector B, and if this is our vector C, the angles are beta here, angle gamma here, and angle alpha there. And then the angle between vector A and the vector B is by making an extension to this vector A, and this angle becomes 180 degrees minus gamma, so this is 180 degree minus gamma. And the angle between vector A and vector C is by extending this vector C. This angle becomes 180 degrees minus beta, so this is 180 degree minus beta. The angle between vector B and vector C is by extending vector B, and this angle becomes 180 degree minus alpha, and this becomes same angle. So by taking those angle between any two pair of vectors, since a plus b plus c is equal to 0, if I make a cross with what we are given, that is a plus b plus c is equal to 0. And then turn by turn, a cross a, then a cross b plus a cross c, that is the expansion of this one, must also become 0. So because a cross a is 0, what happens is, because the sum of these two must be 0, a cross b must be minus of a cross c, and the magnitude of the two must be the same. That is, a cross b must be equal to a cross c. So a cross b is the product of the magnitude of vector a and the vector b times sine of the angle between vector a and the b. That is what I showed you a while ago to be sine of 180 degree minus gamma. Upon expansion, it becomes magnitude of a times magnitude of b times sine of gamma. The same applies for a cross c, and the angle between vector a and c is 180 degree minus beta, and it simplifies to be vector a times vector c magnitude times sine of beta. And because these two must be equal, when they are equal, then vector a times vector b, the magnitude of the product of a and the b times sine of gamma becomes magnitude of vector a times magnitude of vector c times sine of beta. And then if we rearrange, we can easily write that to be vector b magnitude divided by sine of beta is equal to magnitude of vector c divided by sine of gamma. Let us take this one as equation 1, and I will do the same. Previously, I made a cross with the given a plus b plus c is equal to 0 term. Now I will make b cross with it. With the same argument, now b cross a plus b cross b plus b cross c is equal to 0, and because b cross b with itself, any vector crossed with itself is always 0, so b cross a, which is this term, must be in magnitude equal to b cross c. So b cross a becomes magnitude of b times magnitude of a times sine of the angle between b and a, which is 180 degree minus gamma from our previous discussion. So it reduces to this, and the b cross c is the same. It becomes magnitude of b times magnitude of c times sine of the angle between b and c, which is 180 degree minus alpha, which reduces to magnitude of b times magnitude of c times sine of alpha. So by equating these two, because we have said here they must be equal, we get this equation, and upon very small change of positions, we can rewrite that one as magnitude of a over sine of alpha is equal to magnitude of c over sine of gamma. So this is taken to be equation 2, and then this was my equation 1, and this is my equation 2. I want you to remind you with both of them, the same screen, and then by combining these two, because the right side of both of the equations are the same, this is c over sine gamma, this is also c over sine gamma, so we can simply equate this is equal to this, so 3 of them must be equal in fact. So this is actually the proof of what is called the sine law.